Hello, and welcome back to the show. My name's Relevant, this is Do All the Things, and on a previous episode, I was working on the crate Blue Voodoo 60 combo. I'm working on it again today. I'm gonna look at the bias circuit and install some components that I need to install. So stay tuned and find out. Alright, so pulling the chassis out. What is it that we're doing today? Well, it all has to do with the bias circuit, you see. At some point in history, these, oh, look at them. Look at them. Look at them. The current sense resistors on the bias circuit were changed. They're supposed to be 12 ohm, but I found 22. Those are 51 ohms. I've been dinking with it. So basically, I'm gonna put 12 ohms back in there and see what happens. Even though I could fathom that someone upped those resistors to compensate for the fact that this amp runs entirely too hot. It has like just over 500 volts on the B+, which is a little bit unnatural for an amp of this class. Also, if you look over here, when I got this amp, the little piton for the fuse was missing. So the fuse holder was useless. I just did one of these, bypassed it. So I've been running this without a fuse, but I've got the proper fuse holder finally, and we're gonna install that. At least I think I got the proper fuse holder. Oh yeah, that definitely looks like it's fitting in there, bud. All right, we should be good. Finally, this amp will be fused again, except for the HT fuses that I replaced with the resistors so that I could current sense it. Now, real quick, in order to understand what's going on in here, this amp has an auto bias circuit. We don't bias it using conventional means. So basically, what we got going on here is off the power supply, we have this bias circuit. We have one stage of filtration, a dropping resistor, a second stage of filtration, or not necessarily filtration, but reservoir. And you're gonna notice, unlike normal amps, we have two lines coming off the bias supply. Now, off the first section of the supply, that goes over to the current sense circuit right over here. Here's the 12 ohm resistors. Now, these 12 ohm resistors are going to sense current drop based on the cathode's current draw. That was an awkward sentence. Now, say the tubes were pulling, say, 40 milliamps, or the tube, one tube at a time. Multiply that by the 12 ohms, and we get 480 millivolts. So when the positive voltage from here and the negative voltage from there merge, it raises up that negative voltage, which is going to be less negative. So if we're starting off with 62 volts as it stays here, and we add, roughly a half a volt, we're going to end up with the 61.5, right? From there, it goes to this transistor, and that transistor appears to be a PNP. And we know a PNP transistor is turned on by negativity and off by positivity. So as that negative voltage becomes more positive, it's going to close off that transistor a little bit. And that transistor is bleeding bias voltage from the first circuit to ground. So pretty much, whatever voltage drop is seen here controls this transistor, and then that transistor sets your bias. So theoretically, this is what's setting our bias as opposed to the typical potentiometer that you would adjust manually. So one might hazard to guess that whatever we change these current resistors to will directly proportionally affect our overall bias point. So I guess whoever changed those resistors before, that was their attempt to change the bias. And me putting 12s back in, well, I guess we're gonna see what happens anyway. So if we take the screws off the tube holders from this side, this board should lift right out. And if you're ever working on these amps, you gotta mind these contacts here. They will start to get a bit corroded and carbon burnt after time. You should take time to pull them off and clean them, and even maybe sometimes you give them just a little bend there so that they interface tighter. Now we had to take screws off the back panel here. There's a ground bonding screw. There's two for the AC in. There's a couple little guys on the DI out here. And then, all these guys need to come off. That's always fun. Now this should pull right off. Now you kind of have to do that first, or else you're not going to be able to get underneath this board. Question is, if we don't pull the pots off the front and we just remove the board screws, can I flex this up enough that I don't have to undo all this hardware? Because that's super annoying. Let's find out. Yeah, you know what? We might be okay. We might actually be okay here. Like, it's a little tight, but with my technique, I can get at the fuse holder. We just have to jam something in here to hold it up, eh? Consultant? Sure. Let's get in there with this, and we're gonna pull. Might not be able to get the solder sucker in there nice though. Oh, that was good. How about we go through the other side of the hole on this side? Oh, that was good too. Let's see if this fuse holder doesn't fit. Oh, there we go. Kind of flimsy PC mount for something that's gonna take abuse. Well, let's get her on there anyway. All right, we now have a fuse holder. Now we just need a fuse. Spec says 3 amp slow blow, which I've stocked up on. Looks like I could have gotten one to hold the bigger fuses. Wait, is it convertible? It almost just looks like this is an insert that can pull out of there. Well, either way. All right. Yay, fuse. All right, so how about these resistors? These resistomatics right here. These half watts are getting burnt up. So I ordered a fresh set of 12 ohms here. And the schematic, well, what's the schematic call for? It doesn't really say, but I bet you there's something that says quarter watt. These should be 1 watts, 1%, 1 watts. So significantly higher end. Oh, what's this? Glob of solder stuck to the adjacent diode. Glob of solder stuck to the adjacent diode. Now, can we sock on this solder? Oh, that's super effective. Okay, I'm probably gonna do the good old-fashioned component hover for this situation. You know, just like that. Hopefully it still fits onto the chassis. Yeah, it will. It's one of those situations where I don't want to commit to the mod until I know it's gonna work. So I don't want to cut those leads down and then waste some perfectly good resistors. All right, those resistors are on. I'm gonna put at least 2 screws back into place to hold this board down. One of which will be a chassis bonding screw right here. And we'll just balance it out on the other side. So this thing, this is my bias current sense jack. I probably should maybe attach to the actual current sense resistors. Oh, look at that. These sockets sit too proud. Those connectors don't even properly go all the way in. Can you see that? You put it and seat it all the way down. Connectors are sticking like half out. Well, that's a design flaw. Well, so they intended to work that way? Can I shorten those standoffs? Them some long boys. Those are probably 1-inch standoffs, so yeah, these standoffs I have are no shorter. Or are they? Yeah, no, that's the same. 1/2 inch is going to be too short. We're off by 1/8 of an inch. I believe the honest solution to this would be to take these standoffs out, grind them down like 1/8 of an inch, and then seat them back in there. And then of course you would have to loosen up the tube sockets and adjust their height too. Oh boy, no wonder these things glitch out. That's not a solid connection. Yeah, like literally that needs to come down by like freaking, Well, I'd give Crate some constructive criticism if they were still around. Is Crate still around? Oh, Crate. Nobody gives a crap about you anymore. Alright, let's just go put the tubes back in. These JJEL34s. Oh, those are just gonna pop right out, isn't it? Yep. Alright, we gotta get this set up in such a way I can test on it. We got power. We got speaker. We got make sure this thing's still seated. Oh, it's seated crappily. Crappily wappily. Alright, well, let's give it some power and watch it go up in smoke, right? Okay, where's my meter? It's making popping noises. Wonder what that's all about. Let us find a proper ground reference point. And so what voltage we got here? 600 millivolts. See, where is their bias then, sir? R88, R89. R88, R89. 41.7. 41.7. Now it's worth mentioning, there's a Zener diode on here. 47. That's probably gonna clamp this action to some way that I don't care to figure out how to explain just yet. So then, what is our B plus voltage then? 519, 520 volts. Like, come on, are you serious? So if we look at our current sense resistors then, oh, we look like we might have some trouble. If that's 568, 0.568 divided by 12 ohms equals 47 milliamps. Now why does that current sense not agree? 49, 46 on this one. So 46, 49, that math does not sound promising. Let's say for the sake of argument, it's biasing to 30 watts. These are 25 watt tubes. Divided by, it was 520, then multiply that by 0.7 is 40. So we are almost 10 degrees over spec with those 12 ohm resistors. Yeah, I guess I could see what part of the problem here was. What is this snapping, popping noise though, seriously? I never did that before. I'm gonna assume it has something to do with the amp being half put back together. Oh, I see what's going on. Yeah, screw your tube sockets back in. We see these PIDs here have ground paths, and without the screws bolted in on the other side, it's creating a condition which those tubes probably don't have proper ground. So let's just take a moment to fix on that. Now let's see. Yeah, no more clicky poppy. So let's look over our voltages again. Still 518, still 518. You know, we're looking at the schematic here. We're only supposed to get 490. How about this dropping resistor here, R115, 620? Maybe that needs to be a higher value. But then the B plus is coming off of here, right? R115, it's a 620. Man, I just want to pull this voltage down. What's our AC coming off the transformer? 392 AC off the transformer through a full wave rectifier. My quick and dirty math, 392, was it? Times 1.35, 529, yeah. Oof. Oh, maybe we don't have to regulate our B+. Maybe we can keep hammering 512s onto the B+. If we just put some regulation and some dropping on our screen grid, bud. So basically, right here, we make that dropper drop even more. That's gonna bring down the voltages on this end. And then that will tame our screen grid. And by taming our screen grid, that's going to cause tubes to draw less current. So what we need to do is look at that 620 ohm right there. Now, real quick, before we start gutting this pupper, what we want to do is we're going to take some sort of general voltage measurement across that resistor. Should we clip it on to one side of the resistor and then we kind of try to get to the other side? It says she's dropping 18.4 volts. So if it's dropping 18.4 volts and we go and divide that against 620 ohms, our circuit's pulling 29 milliamps, so 30 milliamps spec. Some of that's going to be screen grid, some of that's going to be preamp. There's a lot going on in the preamp. I could see 15 milliamps on the preamp. If, say, we took that 29 milliamps, we multiplied that by, say, a 1K resistor, we would get 29 volt drop. Well, let's see what it takes, because if we clip onto here and we test the other side of this resistor, she's saying 505, and we're supposed to get 490. So we need to drop 15 volts. So we're already at 18.4 plus another 15 volts. We need 33 volt drop total. So if we take that 33.4, then we divide that by the current, which is 29.6 milliamps. We need an 11K. So yeah, a 1K should bring us more closer to target. 12K even, maybe even a 15K. I have 1Ks and 15Ks in stock that will do that. Also, we'll say roughly 34 volts times 0.030 milliamps is only 1 watt. So we don't need the biggest resistors in the world. Really? I gotta double check this math. Maybe we can use up one of these vintage dealies that I haven't got a whole heck of a lot of use for these days. It's giving me 1077. That's the other thing. Can we find an out of spec resistor? Push it more than 1K to come closer to that 11K target? Let us see. Here's some more of those stone bricks. 960, that's under. Oh, this guy. Oh, 1185. I think we found a winner. Another 1185. Holy! So, one of these 1185s. How's our voltage? Do these caps discharge yet? Oh, yeah, it looks like I can no longer get electrocuted from this amplifier. All right, can we flex this up enough to get at that 620? We might be able to reach. All right, let's see. Oh boy, we're just getting cracking and all sorts of. Wow, we're really torturing this thing. Birkin Ceramics is breaking up. I can reach the connection. Problem is seeing it. You gotta get like right down in there. Oh yeah, bud, come on, just a little bit more. This is not that easy to work on though. Really, not like this. Just gonna clear that hole up. I think I got it. I need to go low. Okay, I got it through the holes. I just have to tack it on a bit. I can't get my solder in around the hammer. I think it's safe to say that if I hit my voltage targets, I should take the time to proper take the amp apart and do these connections nice, instead of just half-arsing it. Yeah, now we have to half reassemble it all over again. Okay, we got our wannabe 11K resistor installed because I'm convinced that that's what's going wrong here. It's just the too high voltage is throwing everything off. So as far as voltages go, oh boy, 535, surely you jest. Okay, well, what are we seeing across this resistor? 532, 497, okay. Getting better, we need to bring it down more. Frick, we've increased our voltage. It's probably because of the impedance load the preamp circuit puts on the power supply is being relieved by adding more separation between them. So what's our current sense have to say? 580, 582, 583 still. Still freaking high. Oof. We should see a lower screen grid now though. Yeah, definitely 486. We're seeing negative 41 bias. So how do we bring that number up? Unless we want to go 1.5K here, but Okay, let's check out R96 right here, that 4.7K coming off the bias control transistor. There's Q16, there's our little bias buddy. All sorts of diodes in here. R96, 4.7K. So coming off the transistor side, negative 19 volts, and on the other side, negative 42, negative 19 volts. So what happens if we increase that resistance? Maybe that value's drifted. We're just gonna take a random hundo K here. So either we're gonna cause the transistor to allow more voltage to flow to the negative, or, well, it's bleeding to ground, so increasing that resistance might actually increase our bias. So we will probe our negative voltage here, 41, and with a random hundo K resistor, we will make an ever so slight change to this bias circuit. It does not appear to be doing anything. Still 42 on this side, still 20 on this side. That made a 1 volt change with 100K. We need a better value. We'll just go in there straight up with a 4.7K, cut that impedance in half. It's bringing down the bias, giving us less negative voltage. So we would have to increase the value of that resistor to see the results that we want. Oh, that means going under the board again. Oh, unless you know. Sometimes you can just heat the component from this side and then lift it out. Or destroy the component trying, right? Okay, it's up. We need to get a connection in there. We'll use a similar technique to get this other 4.7K through that hole. Okay, that's connected. Bring her around and mate her with the original 4.7K, effectively doubling our value. Should zoom in a bit for you, eh? She looks ugly, not gonna lie. All right. Now what's gonna happen? Oh, negative 44, 43. We got an increase, 2 volts. So what's that mean for our current draw? Oh, we're down to 480, 481 divided by 12 ohms. Oh, target 40, oof. Yeah, let's double check something here. So what's our B plus? 532, which means we're on a chase, because if we have a 30 watt tube, because it's a 60 watt amp, we can work an EL34 a little harder, times 0.7 max bias, 3940. Oh, we're on target. So we need to double that. I think if I stick a 10K in there, that should put us where we need to be. All right, so I guess that makes sense though, since this transistor, it regulates the amount of bleed to ground for the bias circuit. Increasing the value of that's going to cause the circuit to bleed out less. And we hit target. I'm probably gonna replace that with a straight up 10K. But before I get soldering on this, I want to see if I can tame the voltages a little bit better. I've installed these random dealies here so I can clip different values of dropping resistors. I want to see if I can hit 490 as per specification. So right now, last I checked, we were at 498 or something to that effect. Well, the next logical steps is going to be 1.5K, but not this 1.5K. It's clocking in at 700 something ohms. I actually have a whole bunch of these 1.5K bricks. Well, I can't believe how out of spec these little bricks are. I only have one that actually clocks 1.5K. So let's snap it on there. 537, 502. Okay, still not 490. I don't know how much higher our B plus can go. Screen grid's 495 now. That's not gonna do. All right, what's next? Okay, here's a 2.2K, one of these guys. Now what voltages are we getting? 482. Our B plus has gone up even more. Screen grid down to 478. At this rate, we're not gonna be able to use 6L6s in this anymore. How's our bias looking at least? 371. She's dumped out on us. We might start running in circles here. That's 30 milliamps. We're down to 30 milliamps. This is starting to cause us grief. Okay, so if getting the voltage down to where we need it to be dumps the bias out that hard, what happens if we just kind of put the bias back to where it was? 800, that's a no-go. Well, maybe 30's not so bad. Say we did do 25 watt tubes. 32, okay, that's not too bad. What we need to do is start playing around with the bias resistor value here. I've acquired an 8.2K. These little guys are supposed to be 1 watt. Right now it's 9 point something K. So let's see if we can't attach onto this circuit. 460, 461. Okay, that's 38 milliamps at a B plus of 535. So 30 divided by 5 equals times 0.7. 39. Okay, I think we got the winner. 8.2K here, 2.2K, our new drop resistor. And then this thing should start running roughly where it's supposed to be. But let's plug it in and hear what it sounds like. Now, the reason why I say this is because the preamp was technically overvolted before. And I always thought that this amp had a bit of a muddier tone. Like if you look here, these are some 022 capacitors. I replaced the 047s that were in the circuit because I was trying to prevent blocking distortion, trying to clean up that boosted distortion. Still a little fuzzy. You know what? Yeah, I do think it sounds a bit better now that that preamp voltage has been brought down. Sounds a bit more harmonic than I remember it being. Oh boy, I guess you guys want to know how loud it's gonna go now, because this is the pupper that hit 100 watts with KT88s. How hot? Yeah, they're not getting super hot anymore. Good. 1 watts for the win. You'll forgive me for blocking my ears. Okay, I gotta clip this somewhere where there's voltage. Hopefully that stays put. All right, 535 at 34 is our starting. Let's wind her up. We'll say 70 at 520. Oh, 72 watts. At 515, 82 watts. I'm sure it's breaking up quite nicely. I can't hear as well with this. At 100, oh yeah, she's going 100 watts again. 100 watts, oh, I see smoke. Oh, hey! Our dropping resistor is not having a good day. It's sweating. It's literally sweating, I guess. Oh, we're gonna need more, yeah, okay, so that's great. We got her up at about where we want it to be, and that resistor can't handle it. That's only like a 2 watt. Do I have a 2K and bigger wattage? I don't think that I do. I got maybe a more capable 1.5K. This might not be the solution to our problems then. Hey, that 1.5K brought us to 490, except our tube jumped up to 43. Oi! Oi! I slipped with the tool. You saw it here, folks. That was spectacular. And that is a risk associated with working on these amps hot, which is great because to quote heavy metal, now I'm the one who has to put this asshole back together. Wow. That was wow. Oh boy, there's like black crap floating all around in here. Wow. Is that toxic? So much for that fricking fuse I added, right? Oh boy. You slipped with the tool. It caused arcing. That arcing cascaded and did not stop. R112 got completely chowdered. My test lead's fine. We got stains all over the side of the meter here. I'm not even upset. That was impressive, as the saying goes. Here I was just about to fix this and now I've just made it worse. It looks like this hum balance thing blew out on us too. So according to my tube tester, the tube's fine. It survived, which makes sense because of the nature of this error. So basically what happened is that's pin 3, the anode, that's pin 2, that's the heater. When I accidentally touched those, it bridged, caused a spark, it caused a continuous arc to happen. And then that arc was going through the heater circuit down to the hum balance circuit. That's basically these guys right here. Now I can't find this in here. They don't have the hum balance in this revision. But normally it's two 220 ohm resistors between the two filaments, creating an artificial center tap to ground. That gave the anode a path to ground, probably accelerated by the heater, and kept that train going. So I think we know what values we need here. I think. Oh, I can't remember. Now I gotta patch this all up before I can continue. It's not a big deal. It's just a pain in the ass. But it's an example of what happens when you start getting entirely too comfortable working on these machines, like I am. Start moving too fast and accidents happen. But isn't that classic? It's like the tube socket. I think it's gotten welded onto the board now. Oh boy. Our pins are definitely gotten shorter. Might have to replace this tube socket, but not really because I'm probably going to have to tie wires onto this now and then bypass them because, you know, the trace areas here are completely blown out. On the bright side, our contact pins held up. Also on the bright side, these little rods, these standoffs are too tall by like 1/8 of an inch. And I kind of want to shave those down. What do you think these are made out of? Hard metal? Oh, they might just be aluminum. Oh, they're soft. They're soft, bud. Not even, like 1/16 of an inch they're off. We're getting into it today, buds. Oh, yeah. You know, this was just supposed to be an easy, oh, let's just swap out these components video. But then you get carried away. Shop's already a mess anyway, so we might as well spray some debris around. Oh, on the bright side, I got them all pretty close. Close enough, I think. I think I got some debris in my eye, actually. Okay, well, this general area here is toast. Ah, getting there. You gotta toss it down here. All right, so let's go in for surgery. All right, nurse, we need to go ahead and unsolder this other socket so we can seat her down. Okay, we're gonna put on the screws on the other side to make sure we have these tubes seated the way they're supposed to be. Tube sockets, that is. All right, now let's get those sockets soldered back down. Now I just have to get the broken contacts reconnected here. Basically, we scrape some trace off the board here and make a new solder point. Find our tools that get misplaced in the chaos and reestablish this connection. Assuming it doesn't eventually rip the trace off the board, our sockets are reconnected. All this right here is got to do with the heater hum balance circuit. So, and because our schematic doesn't have this circuit on it, I don't know what value these are. Yeah, this thing's freaking pooched. Look at that, just melted from within. Oh, the humanity. So as for these tube sockets, you know, I could have went like maybe a little bit more, but it's better than it was. So I gotta say mission accomplished. It's gotta be a better contact path now. Oh yeah, it even grips harder. Let's call the consultant wedge back in. Our wedge consultant. Ha 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 ha. Lucky for me, that blown section is right at the edge of the board. So I may not know what the original values are, but I do know how to build a hum balance circuit. So I'm just gonna straight up do what the schematic says right here and put a couple 220 ohms in place. Basically just gonna look something like that. So, uh-oh. Of course we have a bad trace on the board. Why wouldn't we have a bad trace on the board? It's not like we didn't have a thermonuclear reaction. Should be fine for now though. As for here, working upside down and backwards here. All right, let's get the 8.2 in place. And then I think we were good with that 1.5K. I can't remember where we were. I got so derailed by that situation. It's just like, hey, where were we? Oh boy. What were the results that we had? We need to widen those holes. Do this right and you won't completely screw up the trace. All right, the new resistors in place. Now let's get the tube socket assembly in place. The freshly minted tube socket assembly. Let's get a couple tubes in it. All right, we should be about back where we left off. That didn't take me too long, but we're good, I would assume. Ho, 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 boy. Let's give her a whirl on Ernest P. Whirl. Hold on here. What sorcery is this? Oh, the fuse did blow. Tuh, okay. I thought I stocked up on these 3 amp fuses, but apparently I did not. And now I'm gonna have to order more because this is my last one. Okay, we're live again. Let's not make the same mistake twice, right? Right, chassis ground. 537, 537, 497. We're back to 497. Oh boy. All right, well, that 2.2K wasn't sufficient. I'm gonna have to order a special resistor for this. Wow, this is a long going project, eh? I have to order more parts. 571 on the bias. Oh, that's 47 milliamps. Oh, we're back to where we started. Oh boy. All right, so she's all back together now. And that 2.2, well, that's no good to us. But here I was thinking I was gonna have to go ordering on some parts, but I just remembered I just got 4.7K 3-watt metal oxide resistors in stock. So boom, 2 of those in parallel. 2.3K hits target. So now we are seeing 482. It's not quite 490, but that's okay, because our B plus, yeah, it's up to 540. But our bias, 472. That puts us at 39 milliamps. We have hit target, and that should give us 6 watts of resistor right there. Hopefully, that's gonna far surpass that 2 or 3 we had, and it'll be able to hack it now. That said, I don't crank this pupper that often, so we should be okay. But wow, that was an adventure. That was, I hope you were entertained. We had sparks, we had explosions, and then we put it back together again. Crisis averted. The amp is now dialed in, biased correctly. I'm gonna put this all back together tomorrow because I'm so over it for today, but I hope you enjoyed this. I almost thought this video was gonna end on a low note. Really did. Really did. But no, we got her. We got her. Yeah. Except at 540 volts, I don't think I'm sticking just any tube in there anymore. This is more of a EL346CA7 amp, at least to me. That's what I prefer running in it. And of course we could use KT88s, but hey, we're gonna leave it at that. I'm gonna have to relabel this amp on the back so that we know what the story is working moving forward. And I think I'm gonna adjust on this bias tap here so that we can properly see this current sense, not my improvised current sense. And then it should be good. Once again, I hope you enjoyed this. Stay tuned for more, because as of this filming, I do have other amplifier projects coming. Definitely, you're gonna wanna see them if you haven't already, because I don't know what order I actually post these in. It's an adventure to me too. Oh boy.